Just want to go over the system sizer, just what it presented, what it offered. It's available, like we said earlier, it's available as an app, it's available online, and you download it to your desktop. But it's just a calculator. I keep referencing this gentleman's name, Gil Carlson. He was very much involved in Bell and Gossett and the advancement of hydronics years ago, very much involved with ASHRAE over the years. But he had developed a bunch of different things that we started to talk about, we'll continue to talk about, and you'll encounter in your career dealing with hydronic system design and all of that. But he had made this wheel, and I think I briefly mentioned it last week, but he made it out of cardboard for himself. And that was his only intention. It was just a simplicity to access various charts and formulas and stuff that existed in books and tablets and what have you, and you just put it together. And the marketing, the people, got wind of it, and they said, hey, let's put this out to the industry. And so they did. And it's been out for a long, long time. But it's a two-sided wheel, and it has 5 scales. And I don't know if you call it an A and a B or a front and a back, but one side will have scale 1, 2, and 3, and then we'd flip it over and we'd have scale 4 and scale 5. Like everything else today, there's an app for that. So there's an app for the system sizer, the Bell and Gossett system sizer. You go to the App Store, type in Bell and Gossett, and it would pop up. You get 2 things: system sizer in the catalog and the mobile catalog, but just downloading the system sizer. So real quickly, scale 1. It's just referencing a formula that we started looking at last week when we started talking about developing pump curves. And to develop the pump curve, we had to establish flow rates and then pressure drop, head losses, and all. So all it's saying is it's a little bit of a math formula behind the scenes of how to establish the relationship that exists between the load, the BTUs, the delta T that we've selected or operating under, and then the corresponding required flow rate, the gallons per minute. Just some house cleaning, if you will. Just when you're looking at scale 1, they'll have the delta T, temperature difference or temperature change. It's listed from 1 degree all the way up to 200 degrees Fahrenheit. And then in the white band, I call it a band, this white like semicircle, it's listing the load, the BTUs, and it's listed in MBH, millions of thousands, I should say, thousands of BTUs per hour. So if we look at the number 300 in this example here, it's really saying that this represents 300,000 BTUs. That's all. And again, we talked about it last week, not to beat it to death, but the BTU load divided by the weight we talked about, the density, a gallon of water, 8.34 pounds, times 60 minutes in an hour, because we're talking BTUs per hour, and then flow rate in gallons per minute, times the temperature change, the delta T. And that's what scale 1 states, the relationship between load and flow. And temperature drop or temperature rise, chilled water, obviously temperature rise, heating, hot water, temperature drop. So just real quickly, it's just a couple of quick examples. We'll go through it, but it's pretty intuitive. Determine the flow rate required for 100,000 BTU load using a 20-degree delta T temperature change. And it's something as simple as how would you use the scale? How would you use the wheel? And all they're saying here is we're referencing heat transfer and flow rate. So scale 1, determine the flow rate for 100,000 BTUs. We would find 100, which, like we said earlier, MBH, so 100,000 BTUs, and we'd line it up opposite the stated delta T, the temperature drop. In this case here, 20 degrees. Line these 2 factors up, and you can just read in the small white window what the actual flow rate is. So that scale is just doing the formula behind the scenes for us. It's as simple as that. BTUs, opposite delta T, read the flow rate. Yes, sir, CJ. Yes. Yeah, on the flow rate, correct. Yep. Good point. Good point. Yep. Yes. Correct. As you get into it, yes. Yeah. One other quick example. Determine the flow required for 600,000 BTUs, designing it around a 30-degree delta T temperature drop. Again, just math, just plug it in. But 600,000 BTUs, line it up opposite the delta T of 30. Read straight down, it's about 40 gallons a minute. So it's just a quick rule of thumb. We use it, well, it's a bunch of different things. The guys downstairs, inside sales, taking phone calls, trying to help solve whatever. It's a very useful tool. The guys out in the field were out either whether help laying out a mechanical room, out troubleshooting, whatever the case may be. It's just a quick reference. That's all it is. It's just a quick tool. If you were doing a cooling load, if you had a chilled water application perhaps, and you were trying to determine flow required for 20 tons of cooling using a 10-degree delta T, you could use scale 1. And so a couple different ways of getting there, but one of them would be, okay, 20 tons, well, was stated 12,000 BTUs per ton. Times 20 would be 240,000 BTUs or 240 MBH. So I could simply find on this white band again, that 240 MBH. So 200, 250, 300. So increments of 10, 210, 220, 230, 240, opposite a 10-degree temperature rise. And I could read down here and I could find the flow rate. It's just shy of 50 gallons a minute. It's about 48. But one of the things just to highlight, you know, we look at this wheel, we talked about delta T, we talked about the M and what it represented, and obviously GPM and what it represents. Over here, he just highlighted intentionally for cooling applications. And you'll see it listed as GPM per ton. And you got 3 gallons a minute per ton, 2.5 gallons a minute, and 2 gallons a minute per ton. And ideally, it's trying to line up just basically opposite an 8-degree, a 10-degree, and a 12-degree rise. So kind of standards in that chilled water application, and you might even find back at your office or some of the standards, they're probably based it on 10. It's a pretty standard number. Leave the chiller plant at 42, come back at 52. Go out at 40, come back at 50. But sometimes you're going to have a little tighter, an 8-degree, a little more flow rate per ton, or a little wider temperature rise, 12 degrees, a little lower flow rate. But that 2.5 is a pretty safe, pretty standard number. But anyways, scale 1. Just real quick, where's a ton of refrigeration come from? Why do we say that? 1 ton, we say it's 12,000 BTUs. I got a 2 ton, I got a 24,000 BTUs. I got a 50 ton, I got a 100 ton. It really goes back to the old days when they were using ice and for cooling. The heat added to melt 2,000 pounds of 32-degree ice and change its state to 32-degree water in a 24-hour period. It equaled about 288,000 BTUs for the day, or 12,000 BTUs per hour. And it stuck, melting, converting ice solid to a liquid at the same temperature, 288,000 BTUs a day, 12,000 BTUs an hour, became a ton of air conditioning, a ton of cooling, and it just kind of stuck in the industry. One last thing on scale 1, and this is where sitting in your office, designing a job, probably not that important. Out in the field, maybe troubleshooting or help someone troubleshoot or looking at a problem out in the field. You want to know what's going on. What's the actual load happening at this moment while I'm looking at gauges and temperature readings? So it says, you see the water leaving the boiler or boilers at 180 degrees and coming back on the return at about 160. So you determine by checking the pressure drop across the TDV. We talked about that briefly last week, the multi-purpose valve, the triple duty valve, the balance valve. And we've determined that the flow rate is 600 gallons a minute based on the pressure differential across that valve. So then you say, okay, well, what's the actual load? What's happening at this moment? Well, what do we know? We know the flow, looking at the triple duty valve gauges, and we know the delta T. So really, you can kind of work backwards. I mean, it's kind of intuitive. You all probably know the answer, but you say, hey, I know the flow rate's 600, and I know I'm experiencing, I'm seeing a 20-degree temperature drop between the 180 on the supply and the 160 coming back. What's my load? And if you look at it, it's 6 million BTUs or 6,000 MBH. Just a quick glance, but 600 gallons a minute, 20-degree drop, it's a 6 million BTU load. Yes, sir. You would have a chart, triple duty. Correct. What the degree opening of that. Correct. That's exactly right. You would need that information. Some of the newer stuff, much smaller in flow rates, they'll actually come with some like digital readouts. But that older stuff and the larger stuff, you're looking at pressure differential with the degree opening and putting that on a chart or a wheel and saying, okay, what is this telling me? And doing that is how we determine the 600. Correct. Scale 2, it's just moving along. It's talking about, hey, now that I know the flow rate, what size pipe do I need? And when I pick the right size pipe, what's the pressure drop? What's the corresponding pressure drop? Now, back in the day with these wheels, they were limited to two types of pipe that they referenced, if you will. The friction loss for both type L copper and schedule 40 steel. The friction loss on scale 2 is listed in 2 terms. I'll just mention it today. We won't mention it ever again, but one of the measurements or terms was milli-inches per foot. And that was pretty common about 100 years ago. And what it was when you were converting from gravity hot water to forced circulation and you're adding circulators, the pipe size was so large, the pressure drop was so low in feet. It was, not even in feet. So they were using this measurement, this milli-inches per foot, as a means of establishing, pressure drop or feet of head. Today, and what we've been using for quite a few years now, is just feet per 100 feet, and that's scale 2. So when you look at scale 2, right up here would be scale 1, down below is scale 2. You've got pipe sizes, and you're going to line it up opposite a particular arrow on either the copper pipe sizing or the iron, so schedule 40 or type L. You have, again, this white band, which is where we'll find the flow rate that we're looking for. And then inside this, on the top side, is listed in pipe friction loss in feet per 100 feet of pipe. So whatever that number is, it's based on a length of 100 feet of TEL, total equivalent length. And you can see at the bottom here is where they listed the milli-inches. It's just really not applicable today. So just real quickly, again, we'd line up a particular pipe size, trying to find the flow rate in ideally somewhere within this white band or this white, almost like triangle, if you will. And we want to find that flow rate, read straight up, and we can establish what that pressure loss in feet per 100 feet is. So real quickly, from our first example, we had 100,000 BTUs. We figured out a flow rate of 10 gallons a minute. Now we're saying, what size pipe? So what you would do is typically, economically, the guys are trying to use the smallest diameter pipe, right? It's just less expensive, the fitting's less expensive, etc. And that's fine, but don't use too small a pipe. Excessive velocity, pressure drop's very high, so we got to try to find, okay, what's the right size? So a lot of times they'll take that wheel and they'll start from the smallest pipe and they'll work their way until at least at such time that the flow rate we're chasing falls somewhere within this white band. And once it's there, then we say, okay, we're going to pick copper pipe. We want to line up a particular pipe size. So in this case here, 1.25 inches, opposite 10 gallons a minute, I could read straight up. So I get 2 feet of head loss for every 100 feet of pipe. I get 2.5, I get 3 increments, 2.1, 2, 3, 4, 5, 2.6. So all that's stating is if I have 1.25 inch copper pipe and I'm pumping 10 gallons a minute through it, for every 100 feet of pipe that I have, that the resistance, the frictional energy required is going to be 2.6 feet developed by the pump for every 100 feet of pipe. That's all it's stating. It's establishing the frictional resistance. I have a flow rate of 70 gallons a minute in a typical hydronic system. What would be the BTU load? Now, back to what we talked about last week. Quick answer, it depends. Can I get back to you on that? So typical hydronic, most people would read that probably hot water heating. So say we're talking hot water heating, 70 gallons a minute. Standard system. We kind of said as a rule of thumb, or beyond a rule of thumb, but what would be a typical delta T temperature drop in most hydronic heating systems? So what would be the BTU load of 70 gallons a minute? We could do the long formula. We could do the short formula. Or we could just take the wheel. And what scale would I look at? Yeah, 700,000 BTUs. Yep. And so a couple different ways of getting there. 70, opposite the 20-degree delta T, figure the load, find the load, or 70 times 10,000, which is what? 500 times 20, which is what? 8.34 times 60 minutes. Specific gravity of one, specific density, specific heat of one. But the wheel is pretty simple. But anyway, so then it says, hey, what size pipe to support that 70? After I've established, hey, I got a 700,000 BTU boiler down in the basement. I got to pipe it. It's got to go somewhere. What size pipe am I using? So same thing. You take that scale and you're going to start. In this case, we decided we're going to settle in on iron pipe size. So the first pipe size that we come across where that 70 falls within this white band or very close to it would be right here. 70 is 2.5-inch iron. So that would be a selection. Then you say, okay, if I look at this and I read it correctly, 70 gallons a minute, read straight up, it's basically about 3.5 feet of head loss, pressure drop for every 100 feet of pipe of 2.5-inch iron flowing 70 gallons a minute. This is kind of one of those strange examples where it happens maybe more often than we think, but where you could actually pick two different pipe sizes and they both technically would work. I'd go to the larger size, right? And if I use that larger size pipe, what's the benefit? Less energy loss, right? Head loss, right? Larger diameter. Same flow rate, it's going to be less pressure drop. So, maybe from an energy consumption, what's the downside of going to 3-inch? Yeah, cost, upfront costs, installation costs, upfront costs, first costs, all of those. So do I spend a little less money with a smaller diameter? Operational costs might be higher, consumption of energy. Or do I spend a little more money up front, but over the life of the system, operational, maybe it's a little lower cost. So those are just things to be aware of that you kind of balance out. What's the goal? What are we trying to do here? But same thing, I line up the iron pipe. Next size after the 2.5 would be the 3, 70 gallons a minute, read straight up, 1.1, 1.2 feet of friction loss for every 100 feet of pipe. That's what it's telling us, scale 2. Simple, easy. Scale 3, all it talks about is how fast is the water moving. Scale 2 we just talked about was pressure drop. What's the frictional resistance as the water rubs against the inside wall of this pipe? This one says, well, how fast is it moving? Feet per second. It's the one time when you have the wheel, if that's what you're using, where the two scales work together. Generally speaking, scale 1 is independent from 2. 2 and 3 do work together. Flip it over. 4 is independent. So they don't all have to all line up. It's just the one time when you use the wheel that 2 and 3 do work together. The way he built it, designed it. And so basically we're saying, hey, the water velocity should be high enough, but not too high. High enough to carry any type of air, any kind of entrained air in the system. We want to get rid of that air out in the system and bring it back to the boiler room. where we can heat it, pass it through air separation, and get rid of it, eliminate it. But then we also don't want to have it moving so fast that maybe it creates a noise concern. Now, if you're in a manufacturing commercial building where there are all kinds of noise, that's less of a concern. You're doing an apartment building or a dormitory or a hospital operating rooms or whatever, and something turns on, you don't want to hear that water moving through the pipe. That would be unacceptable. It would work, but it'd just be unacceptably noisy. So we have these, like the minimum flows and the maximum flows, typically feet per second. So that's what scale 3 is all about. So like I said, this is the one time where they line up together. Whatever I established in scale 2, picking a pipe, figuring 70 gallons a minute, what's my pressure drop? Okay. Then I could glance down, and that's what we do. Once you line up that 2.5-inch iron pipe with on scale 2, find 70 gallons a minute, which is now right down here on scale 3. And when I find the 70 in this example, I just read it until I intersect that scale. And the velocity is about 4.5 feet per second underneath the 5. Perfect, fine, no problem at all. If I was going back to that 100,000 BTUs with that 10 gallons a minute through 1.25-inch pipe, 1.25-inch copper, 10 gallons a minute, read down here. Where do I intersect? Just under 2.5. Fine, fast enough, not too fast. So all this is a quick check. Like flow rate, delta T, okay, got it. Pipe size, got the pressure drop, just real quick. Okay, he's not moving too fast. Move on. Just a quick check. And it's all based on just some, industry standards of what would constitute water moving a little too fast and creating velocity noises. What's the velocity of 1,600 gallons a minute flowing through 8-inch pipe? So what would I do? Scale 2, I line up 8-inch pipe. I really don't care where the 1,600 falls up here because I'm really not chasing after the pressure drop. I want to find out the velocity. But once I line up that 8-inch, I glance down to scale 3, find 1,600. So 1,000, 1,500, 2,000. So I'm going to say just a little bit above that line is 1,600 gallons a minute. That's pretty excessive. That's close to 10 feet per second. We typically don't want from a noise, from an erosion, corrosion, we don't want to be above about 8 feet per second in steel pipe. So that technically, even though from a pressure drop standpoint, you say, it's not that bad. It's whatever, 3.5 feet per 100, but the velocity is quite high. And so maybe I'd have to go through, be forced to use a larger diameter pipe. So in this case, I'd just move the wheel on scale 2 to 10-inch pipe. Do the same exercise, find 1,500, there's 1,600. So about a little over 6 feet per second. That's very acceptable within the industry standards. And you guys probably have all these charts already done for you. Back at the office, I'm sure they have tables or software was taken care of. It's just knowing where it was coming from. And again, B&G and the plastic wheel didn't invent this. They're just taking all the information that exists in different charts and Moody's pressure drop charts and what have you, and kind of put it all together. Of all the scales, this is probably the least useful. And what I mean by that is it's basically just a calculator. Now, back in the late 50s, early 60s, when this thing first came on the market, not everybody had a calculator. 60 years ago, 55 years ago. Today, you have them on your watch and anywhere in between. Your phone, your iPad, God forbid someone has a calculator, but so it's the need is long since gone. But it was just a wheel or a scale to use as a calculator. So just reading through it real quick. What's the pump head based on the resistance per unit length? So what did I find in scale 2? And then, hey, what's my total length of piping? 60 feet, 6,000 feet, 250 feet. What is it? And that would help me calculate the total pressure drop. But there's one comment here. Total equivalent length, TEL. Fittings, I think we touched on it briefly last week. Fittings have a maybe a greater resistance to flow than a straight piece of pipe, or there's an equivalent length of straight pipe to equal what that pressure drop is of that 90, that T, that 45. So there are tables, and in fact, on the enclosure of the wheel, some of you might still have it here, on the backside, and of course it dates itself with the fittings that they're using, but they would have listed out saying, hey, a regular 90-degree elbow screw, steel 2-inch pipe might have an equivalent TEL of 8.5 feet. So one 2-inch 90 might be equivalent to 8.5 feet of pipe. So either we sit down and we figure out all the fittings and we add it up and we add it to the straight runner pipe, and that becomes my TEL. Or what happens a lot of times in the industry, especially when you're out in the field and you're kind of doing a design build and a lot of stuff might be existing, is we'll figure out that total length of run and then add 50%. And that will become my TEL. And that's a way of accounting for it. It's probably a little aggressive, a little safety factor, but it gets you, in the ballpark of what the total length of piping should be, and then do our calculations. So anyways, scale 4. We blow it up. Here is our total length of pipeline. What's the length of piping in that white band? This information right here is going to be the calculation. That's what we're going to calculate. And what happens is that piping friction loss feet per 100 feet, that's coming from scale 2. When we figured out scale 2, what size pipe, what's the pressure drop per 100 feet, that's this number here. And we just want to line that answer opposite how many 100 feet of pipe do we have, or how many 50 feet, or how many 1,000. And again, someone can just sit down real quickly. Most of the time, right in your head, you can figure out what it is. But back when there were no calculators, it might have been a little more useful. So it's just a quick example. Use scale. We got a total pressure drop of 10 gallons a minute of 200 feet of pipe. 200 feet of straight run of pipe. So the first thing I want to do is I want to add that 50% because I don't know what the fittings are. I haven't listed them. So I'm going to say 200 times 1.5. Okay, I got a 300 feet of TEL. And I'm going to line it up opposite the pressure drop of 2.6 that we found on scale 2, opposite 300 feet. So 2.6 opposite 300. I read here, the answer is like 7.5 feet ahead. It's just doing math. Just a quick calculation. And we don't need to keep going through these different exercises. But scale 4, it's there. It's a calculator. Scale 5. This is pretty good. This is a good scale in that it's very useful for talking about flow and head, the change in head based on the corresponding change in flow. And we started talking about it last week when we maybe mentioned a little bit about system curves. And we're certainly going to talk about it more when we get into variable speed pumping and how this all relates. So scale 5, based on the relationship that exists between flow and system pressure drop, system resistance, head varies approximately as the square of the change in flow. And there's that formula we talked about before. Scale 5, this whole scale is built on this formula. A known flow, have a new known flow with a known pressure drop. I introduce a new flow. The change in that flow, whatever that answer is, squared times my original head becomes my new pressure drop. So a manufacturer of a chiller says, hey, I know that when I've tested my chiller, the barrel, it will offer about 12 feet of pressure drop when you pump 100 gallons a minute through the chiller. So 100 GPM, 12 feet of head loss. And the guy says, hey, I want to try to increase the capacity. And the manufacturer says, I can pump more GPM through it. What's the head loss at 150 gallons a minute? Now we could sit and do this formula and say 150 over 100. What's that squared times the original pressure drop of 12? There's my answer. I could just take scale 5 and say, hey, I know 100 opposite 12 feet ahead. So here's my feet ahead on that scale in scale 5. 10, 11, 12, opposite 100. Without moving the wheel, just find 150, read straight up. About 26, 27 feet. So it's just a calculator. This wheel is set up based on this formula. So it's very useful. It can be useful. Plotting system curves. And again, today, software selection programs that you guys using all the time, whenever you're plotting or picking pumps, it's automatically going to do this for us. It's going to build that system curve. But as you're sitting there looking at it, just know where it's coming from. The system curve is based on a known set of conditions. You calculated a load of 200 gallons a minute, or 2 million BTUs, and you calculated a pressure drop of 30 feet. So I know I need 200 gallons a minute to move this load, and I got to overcome 30 feet of resistance. So you can then plot a curve if you wanted to. And one of the easiest ways, again, with this scale, and the computer does it for us anyways, but you could take the known flow and head loss. So in this case here, it's circled or highlighted, 230. 200 gallons a minute, opposite 30 feet ahead. Don't touch the wheel. Just find some other corresponding flow rates and then what their pressure drops would be. So if I have 200 opposite 30 and I go and look for 300 gallons a minute, I see the flow is 60, 65, there's 70. It's just shy of 70. So do the math, it's about 67. 150 gallons a minute straight up, 17 feet ahead, 100 gallons a minute, 7. So it's just plotting the math for us. Very simple. And you build a system curve, and you'd want to see where that curve intersects the pump. One other thing on scale 5 is valve manufacturers have this coefficient, this pressure drop, this C sub B rating. So control valves, all valves, but specifically in the industry where we're trying to maybe control output of fan coils or heat exchangers or whatever, we select these valves based on perhaps their C sub B rating. And when you look at CV, what is it telling us on that valve? Whether it be, Honeywell 3-way mixing valve, reset valve, Johnson Controls 2-way, whatever it is, they all have a CB rating, C sub B. And but the CV just states the flow across the valve and flow rate in gallons per minute. That creates a 1 pound pressure differential across that valve. It's that straightforward. When you look at a CV and it has a number of 10, it's saying, hey, this manufacturer tested it and he had to move 10 gallons a minute through that valve. That would create a 1 pound pressure drop. So if I increase the flow, knowing this relationship of flow and head, or I decrease the flow, I know what the new pressure drop, increase or decrease, is going to be because of that mathematical relationship. So from a visual standpoint, that might state it a little cleaner or clearer. Flow rate, CB, is the flow rate that causes a 1 pound pressure drop. Or we say that relationship of 1 pound per square inch is equal to 2.3 feet of frictional head loss. So what's interesting is when you look at the scale, before I get there, and this is just kind of a cartoon drawing, but it's a visual of how the valve manufacturers test their valves so that they know when they state it, this is how they got there. So they're saying a typical valve test, water level remains at a constant 2.31 feet above the valve inlet to maintain a 1 pound inlet right here. 0 on the outlet side. They have a container where the water is, collecting, if you will. The pressure at the valve outlet is 0 psi. The volume of water flowing for 1 minute can be weighed to determine the flow rate. And that's how they would test and say, hey, I did 6 gallons a minute, I have a CV of 6. I did 20 gallons a minute, I have a CV of 20. That's what that valve is rated for. That's where they come up with this CB. So there's a control valve to be selected for 3 psi differential at a flow rate of 2.9 gallons a minute. So maybe you have a bunch of, say, chilled water fan coils scattered throughout an office building. And to get the performance out of this particular load in this office area, he needs 2.9 gallons a minute. That's pretty detailed. It doesn't have to be quite that, but that's the statement that the engineer came up with, 2.9 gallons a minute. And the control valve is to be selected to create a 3-pound pressure differential. You guys ever hear or get involved, or maybe in a conversation where you get into the conversation of control valve authority? I'm sure you've, okay. I'm sorry. Control valve authority. Control valve authority. And all it's stating is when a valve, like a control valve, say it's modulating, open or close is set point, open, close, I'm satisfied, I'm not. When I'm modulating, the reason I'm modulating is I'm trying to control something. Maybe the discharge air temperature on a makeup air coil, hot water leaving a heat exchanger, whatever it is. I got this control valve controlling the flow, maybe through a heat exchanger, and I'm looking at the downstream, the outlet of what I'm trying to measure, what I'm trying to control. When that valve goes to throttle, I want to have an impact on the output. If I'm saying I'm starting to get too hot, then I want that valve stroke to take place. It better have an impact. So if I provide a valve that has a fairly high pressure drop, it has better valve authority. As it strokes, it really impacts the flow, which impacts the output of the heat transfer, air or water. So that's why a control valve might be selected with this 3 PSI differential to control 2.9 gallons a minute. What's the CV? Yes, sir. If you were looking for, better control performance of that control valve, as that valve strokes, as it's modulating down or open, but say down, I'm trying to satisfy a certain water temperature or air temperature. As I stroke, I really want to reduce the flow going through the valve into that heat exchanger or that coil or whatever, wherever it's going, so that I really impact the output, the heat transfer of that heat, the heat exchanger, whether it be makeup air coil or a hydronic, hot water, shell and tube, water to water heating, whatever the heat transfer is. The point being that a lot of times using water flow rate is very non-linear, the output. You need a really high delta T, which means you got to really reduce the flow to have performance change downstream. So if I have this kind of non-linear, and then I introduce this really high pressure drop valve, and so as I stroke, I really crunch down, I really throttle down on the flow rate, that'll have an immediate impact on the output downstream of the better, much faster reaction, much more accurate. Right, correct. Simplify is what you're saying. Keep it simple. Yeah, control valve authority. Right, exactly. Right. Yeah, like sometimes, and get into all different examples, but that's why you might see someone specify something like, geez, 3-pound pressure drop across 2.9 gallons a minute. But it could be for that. So now you get out into the field, and a lot of times the engineering is the hole method. What size hole becomes the valve? So a 2-inch pipe, steam, water, whatever, flowing through, makeup air coil, heat exchanger, whatever. And now I got a valve that can handle a hell of a lot more than when I'm actually moving through in this 2-inch pipe. So a lot of times when you look at control valves, you might see like a 2-inch pipe get throttled down to say 1.25 inches, and they'll blow back up to 2-inch, because I need the 2-inch for the flow, but I want the valve authority, the control. So when that downstream capillary or whatever's measuring says, hey, I'm starting to get warm, when that valve goes to close, there's an impact, a performance, a much more accurate decrease of output. So you don't overshoot, because then the valve goes, he hunts and he shuts right down because he overheated. And then the discharge temperature or the water temperature drops and you open it back up. And then he overheats and he's doing that, hunting. Yeah, glow valve style, get into what the internals look like, but more of a glow valve, but a valve that has a low CV. So, because if I have a valve with the high, two valves, two-inch valves, one has a CV of 40 and one has a CV of 20. Well, I need to move 40 gallons a minute through that valve to create this 1 pound pressure drop. That's how that valve got the CV rating of 40. This guy here, I only had to pass 20 gallons a minute. So he's probably got a smaller orifice, maybe a little more with creating that 1 pound pressure drop. So that manufacturer says, hey, my CV's 20. This guy says I'm 40. Now, when you're talking to the industry, doesn't know either one, but when you're getting into, okay, I want, now I'm designing, now I'm trying to have performance, I'm trying to provide something. That's where it becomes important. Now, if I'm a big three-way mixing valve down in the mechanic room and I'm feeding 100 apartments upstairs, well, I don't necessarily want a huge pressure drop, because it's not NASA. It's a change in the water temperature. I'll take some return water, blend with the hot boiler, and and I'm not creating this huge pressure drop because usually on the other side of that valve is my distribution pump. And I don't want to create a huge pressure drop on the suction of a pump. So it's not like one size fits all. It's just what's the application where you really want to get critical. And so something so small like this is probably pretty critical for performance. And so the way to use it and to get there, 3-pound pressure differential to create to control a flow rate of 2.9, you'd say, hey, what's the CV? So we're kind of working backwards. We don't know what the CV is, but what we do know is when I move 2.9 gallons a minute through that valve, it better create a 3-pound pressure drop across the valve. So the way I would read that is I'd go find my flow rate, which again, GPM in that white band on scale 5. So 1 gallon a minute, 2 gallons a minute, 3 gallons a minute, back it up, 2.5, 6, 7, 8, 2.9 gallons a minute. And then notice here, again, I got to clarify. On this scale, top side is listed in feet ahead. And the bottom side is in PSI, pounds per square inch. The other thing to notice is, see that letter C sub V, CV, CV? They're opposite each other, which they have to be. So we were talking about it earlier, but like in this quick drawing here, apologize for going backwards. 1 pound pressure drop, 2.3 feet ahead. So when I look at that scale, 1 pound pressure drop, one on the PSI side is the same as saying 2.3 feet of head loss on the feet of head side. So I'm going to go and I'm going to say, hey, 2.9 gallons a minute, opposite 3 PSI. So those are the conditions I'm chasing after, 2.9 opposite 3. And all you do is you read back and you find this, what's the number right here? So I got 1, 1.1, 2, 3, 4, 5, 6, 7. I would look for a valve manufacturer that states their CV is 1.7. So at 1.7, that says, hey, when I flow 1.7 gallons a minute through that valve, it creates that 1 pound pressure drop. That becomes my CV rating. And that's a standard in the industry. Whatever the flow rate is to create 1 pound pressure drop. When I take that orifice and now I stick it on the supply pipe going to say a chilled water coil, and I'm pumping 2.9 gallons a minute through that orifice, it's going to cause a 3 pound pressure drop. So the engineer got his control valve that he wanted based on CV. He didn't state the CV. He said, this is my set of conditions. Tell me what CV valve I need, what valve with the CV of what. And again, it's just all about this math relationship, flow and head. Change it, I can calculate the new pressure drop. No, you've exceeded your limit. Talk to you next week. Of course you can. What do you got? Like a control head. I don't know. I'm not sure, but I think we're going to go there because we're going to get into variable speed pumping where we have control head that we have to account for. Yeah, but there is a reason. I mean, I think the reason I'm going to discuss is going to maybe correspond to the kind of industry statement that's said quite often, that there's going to be some pressure drop. There's going to be a control valve pressure drop relative to the overall system pressure drop. So that was System Sizer. Sorry that it took longer than I thought. I apologize. But and again, we don't have the wheel in front of us, but it's a pretty useful tool just for explaining a lot of different things. Let's see here. You guys can see that. I'm assuming the other guys can as well. So kind of a silly statement, but why is it doing that? Do that. Why variable speed pumping? You guys get involved with it at your office already, I assume? Yep. Why? Why do we do it? What's the benefit? Or is there a benefit? We do it because we're told to do it. Say it again. As you go to partial load. Absolutely. That's exactly in a nutshell. Class dismissed. See you next week. Why variable speed? So in that packet, not packet, that 3-ring binder of all the engineering manuals, one of them, I'm sure you've read through all of them already. So one of them is about variable speed, variable volume pumping. And actually Bell and Gossett, not that they invented Mother Nature, because Mother Nature was ahead of B&G, but they took that fact about partial load, change the flow, change the corresponding pressure drop, and what kind of impact that can have, energy consumption, et cetera, et cetera. So at the very beginning, when systems were designed and variable speed wasn't a player yet, this is how they probably would have designed systems. 2-pipe control valves. At that time, it would have been a 2-way control valve, whether it be modulating or open close, chillers, primary, secondary T's, et cetera, distribution pump. And so before they had the variable speed pumping, they would have these control valves. And the problem was, say, a set of conditions. I got 1,100 gallons a minute at 100 feet ahead. And I got a control valve of controlling one of these terminal units. And these terminal units could be anything, right? It could be buildings, it could be 3 different buildings split up over 1,100 gallons a minute. It could be individual terminal units, hundreds of them. But I got a control valve pressure drop at 20 feet ahead. That's good control authority on that terminal unit, on that heat transfer. And what they're trying to show here is on a constant speed pump, before we introduce variable speed technology, here's my condition, 1,100 gallons a minute at 100 feet ahead. Here I am out on this curve. And then a bunch of the valves close because they're satisfied, space temperature satisfied. There's no speed control. The pump backs up on its curve. That's what it does. It's the only thing it can do. It follows the curve. There's no speed control. But if the number of outlets, circuits, zones close off, I'm dumb. I just kind of develop as much as I can. And what happens is at that flow rate of 550, I actually develop a little more pressure drop, 110 feet ahead. But as I reduce the flow, a lot of the piping, the equipment, and everything, that head loss is variable. Like if you reduce the flow, you reduce the pressure drop. But you still have this control valve. that under design conditions was sized to control about 20 feet of pressure drop across, say, a terminal unit. And as you back up and you develop in this 110 feet, and these guys, the pressure drop, that squared relationship. Think of scale 5, change the flow, change the pressure drop. It's a squared relationship. So this, 100 feet ahead, as it's reducing, it's cutting down, it's almost a quarter of the pressure drop of what it was at design flow. Half the flow, a quarter of the pressure drop. This control valve is now absorbing almost 90 feet of what this pump can develop, 110 feet ahead. Very challenging, very noisy. Maybe the valve, the actuator might not even be able to close or control against that, and it might pop open. And if it can control, you're still going to have a lot of velocity noises. It was very unstable operation. And this is what they were wrestling with as these systems developed and they got bigger and more accepted and all of that. And so this is just a quick example of maybe a more modern cartoon drawing, but it's kind of showing the same thing. System pressures in a constant speed pumping example. I got a pump that's pumping 100 gallons a minute and can develop, say, 100 feet of head. Suction is 20 feet, discharge is 120. And then as you encounter different pressure drops and you look at the gauges, that 120 feet is starting to dissipate. I got 10 feet of pressure drop across this terminal. I got 10 feet across the control valve, more piping, maybe more radiation. I get back to 20 feet on my suction. Same thing, constant speed, but now that flow rate's in half because half of those zones closed. He's developing, only pumping 50 gallons a minute instead of 100, but he's up about 115 feet of pressure differential. And again, it's just another visual, but saying, hey, this control valve's now trying to absorb 92 feet of head. Very, very aggressive, very challenging, very noisy, and it just led to a lot of system operational. So one of the first things they did is they put three-way valves in. What would be the benefit of the three-way valve? Yeah, constant flow. It didn't change, whether the valve was in the terminal unit side or the bypass side. What are these balance valves for? What would they have needed them? So that no individual system. Yes, at the end of the day, that's what they wanted to have happen, is that to provide that constant flow, that constant volume. Yes. It's the exact same pressure drop. There you go. So whether I'm going through the coil or I'm going through the bypass, that bypass valve was to try to simulate the same pressure drop as the terminal unit. So the pump didn't see a change. So it had volume. Problem was, it was a considerable amount of waste of power. I mean, it took away some of those concerns that they had with the high pressure drop across the control valve. It did that, but you were consuming a lot of energy. And again, this would just be like a more modern drawing of the exact same thing, three-way valves. But eventually, obviously VFDs showed up and all of that. This is just showing a three-way valve. You can have a couple of different scenarios. This is saying maybe 100% open to the terminal unit. So that flow is not going through the bypass. It's all going through. So that port there would be closed. All the flow's going through the terminal unit. If you were satisfied at set point for whatever reason and you close that port, now all the flow's going through that bypass. So we'd want to make sure that balance valve simulated that pressure drop to achieve that same volume of flow. Again, waste of pump power, so to speak, but it operationally, it didn't affect the control valves negatively. Over here, it's another discussion. There can be some reasons for balancing, because you can use that pressure drop of that valve as part of your balancing one circuit versus another circuit. Yeah, they're all. return side, yeah. We can get down there. Yeah, that'd be a sidebar. Um, so variable speed. So it gets to these pump affinity laws. Very exciting stuff. But all it's saying is that mathematical relationship allowing you to predict the flow and change, the flow and head, and the horsepower required. If we were to change either impeller diameter at a constant speed or change the speed with a constant impeller diameter. So for the most part, variable speed pumping, it's this, changing the RPM with that fixed impeller diameter. And so there's like these three statements, if you will. The pump capacity varies directly as the speed change. So you double or cut in half, the flow rate doubles or is cut in half. Now, as I get into this, showing it right here, two things. One, you're going to have this copy of this PDF, but the other thing is, again, back to that 3-ring binder. One of the manuals talks very specifically all about the pump affinity loss in that relationship. This is scale 5, really. The pump head varies as the square of the speed change. So I have a certain flow rate and I double it by doubling the speed. Okay, I double the flow rate, but I quadruple the head loss. Or conversely, I have a certain flow. I cut the speed in half, I cut the flow in half, but I cut the head in by quarter. I reduce the head loss. So it would be the resulting pressure drop of that remaining flow going through that piping system. Yeah, correct. Yeah, yeah. I think you're checking up on me. And so then the third law, if you will, flow rate 1-for-1, head loss squared, and then a brake horsepower requirement, it varies as the cube. And that's, to your point at the very beginning, why variable speed? Energy savings. I can reduce the amount of energy required, and it's a cubed relationship on changing the speed, reducing or increasing, but most importantly, have this design point that we hit very few hours of the season, and then I operate something less than that, and I can really knock down the required flow, which is great. Cuts reduces the head loss by a square, and then reduces the pumping power requirements by a cubed relationship, which at the end of the day is electricity coming in to power the motor, which is a utility bill, for the building owner, the property management. So this is kind of, whether it be diameter. Now, years ago, it wasn't that uncommon to take impellers and take them out and trim them, cut them down, or whatever. It's old school. Today, it's all variable speed by changing the speed. So you might have that fixed impeller diameter based on that design set of conditions, and then let the VFD drive do its thing and vary the speed to the set of conditions that are actually happening in that building or in that space or in that, that at that moment. So looking at some curves just real quickly, we have this thing, I think Willie will probably touch on it a little bit next week, but we have some software, system software selection program from Bell and Gossett. And so this was just a couple of quick examples that said, hey, if I had conditions of 100 gallons a minute at 100 feet ahead, plugged it into that system-wide software to pick a pump, it picks a particular model number pump at a speed of 3450 RPMs, 100 gallons a minute at 100 feet ahead. So then you say, hey, and I'm just looking at trying to build a case for this variable speed. If I cut the flow rate in half, 50 gallons a minute, which means the corresponding pressure drop is going to be a squared relationship reduction. It's down to 25 feet ahead. Plug that in, pick a pump. It actually could pick the same pump, but it would select it with a different RPM. So from 3450 down to 1725. So here is my 50 gallons a minute vertically. horizontal over to my pressure drop. Here's my 25 feet ahead. So two different pump curves. It's the same pump, but two different speeds. So then you kind of read this whole pump affinity law exercise we just went through, and the flow rate, cut it in half, cut the speed in half. It's a 1-to-1 relationship. It works. Well, now I go back to that software and I say, I want to pick a variable speed, not a constant speed. I want to pick a variable speed pump. And so 100 gallons a minute at 100 feet ahead. Here's my maximum, 3450 RPM. Here's my impeller. This is the pump efficiency. And then I have this system curve where I'm reducing the flow down to 50 gallons a minute at 25 feet of head loss. So I'm taking this one pump and I can go from that design set of conditions and then all the way down. And typically, like last week when we were talking about pump curves and all that, we'd have different impeller diameters. And what we're showing here is different speed curves instead of the impeller diameter. It's the same fixed impeller. I'm just changing the speed. And as I change it, I'm changing it because of system conditions that are allowing me to do it. I can consume, less horsepower and require less horsepower to move the 50 gallons a minute because the pressure drop is so much less than at that design condition of the 100 gallons a minute at 100 feet ahead. So that's what variable speed pumping, when we do selections, you guys are doing it all the time. That's the benefit, or one of the benefits. It's the same pump with just multiple, almost an infinite number of speed changes and the corresponding performance. So you look at these speed curves to tell me or tell us what the pump can do. So back to that, constant pressure, real quick. That 100 at 100, corresponding pressure drops, reading the gauges, 10 across the terminal unit, 10 across the control valve, additional pressure drop back to my 20 feet on the suction of this pump. With a variable speed pump now, and I have a load reduction, so I'm dropping the flow rate down to 50% of 50 gallons a minute. I have that control point of that control pressure drop, control valve pressure drop of 20 feet, DP set for 20 feet. So I got to maintain 20 feet across this, say this terminal unit. That's my control head. But I can take this pump and I can back it right down. The corresponding flows, like you do the math real quick in your head, or you take that scale 5, but 100 gallons a minute, I'm creating a 30-foot pressure drop. I cut that flow down to 50 gallons a minute. I don't cut the flow in the head loss in half. It's that squared relationship. So it's 7.5. It's a quarter of 30. And the same thing all the way through. So here it's just showing a quick example. And again, this is just kind of another way of looking at that formula, but it's just saying the flow is a 1-to-1 relationship, the head is a squared relationship, and the power consumption or power requirements is a cubed relationship. And then this is just saying percentage of reduction of head and required horsepower. So it's just stating these pump affinity laws apply to variable speed pumping. So out of the ASHRAE book, and that's one of their, it's been stated for quite a while, but it's a standard, right? I mean, I think it's 2 horsepower or greater has got to have some type of VFD on it, basically, because they know the potential for energy kW savings by reducing the consumption. So it's standard practice. It's just a little bit of, okay, why? What's going on here? Why are we doing this? And these will just be some visuals, variable primary. So I've got, I don't have primary secondary here with boiler pumps and distribution pumps. I'm using this pump to provide flow through my boiler plant as well as through my terminals. And I've got maybe some type of VFD drive with some remote DP sensor that has that control head says, hey, I need a minimum of 15 feet or 20 feet or whatever that number is. So as I'm ramping this pump down, don't go below, maintain that minimum 20-foot head loss to ensure proper flow through the coil and the control valve. Um, one of the things we touched on as far as selecting pumps, and Will had touched on a little bit last week, where with these variable speed applications becoming such the norm that it's fairly common, you got this BEP, that best efficiency point that the manufacturer states, that we start selecting that pump maybe just a little bit right of that. And you start looking at that system curve. And then what you find is, and again, one specific impeller diameter, and we're just having various speeds, so different RPMs, which means performance curves are based on the speed change. But we're following the system curve. And you notice that we're not going down, they're not taking the system curve down to 0, because we have this control head stated at, say, 20 feet. So I'm going to start my system curve for my piping and my chiller pressure drop or boiler pressure drop or heat exchanger pressure drop. It's going to start, I have to develop that, based on maybe this feedback here. I got to maintain that 20 feet. That's a given. That's not going to fluctuate. So when I do that system curve, it's starting at that low point, that 20 feet, and developing my system curve. So I can operate, all the way down, and you achieve, relatively speaking, high pump efficiencies achievable at these low speeds. Because when you pick the pump, you kind of picked it just a little bit right, because we're not living here. We do those bell curves and those, low profiles, all the different fancy terminologies they will use, but very rarely are you at design conditions all the time. So you're typically going to be living somewhere in this range here, and you're operating with fairly high efficiencies, which means you're consuming the least amount of energy. Did you have a question? Yes. Yep. Uh, uh, yeah, for a particular, either maybe the furthest reaching or a critical, one of the fan coils, whatever the terminal unit is that has a control valve, and I want to maintain a minimum pressure drop across that to ensure proper flow. So that, whereas before, like especially when they went to the three-way valve, it was um, to eliminate that massive development and pressure differential from that constant speed pump on that one remaining control valve that probably couldn't even handle that high pressure differential. Well, what the variable speed would be like, as the I'm showing 3, make it, 75. And one of them has, or maybe they're all, and we're just saying, hey, a far reaching, as he's reducing down, I don't want him to get down to 0. I want to make sure that I can reach that furthest terminal unit, furthest point, and overcome the pressure drop of the control valve in, in the terminal unit. So when I say I'm variable speeding, this is going to be, this is my bottom rail. I'm not going to go below this. But from that bottom rail up to my design conditions of, say, that 100 feet, I'm going to vary, and that's where my energy savings is going to take place. But I'm not going to go down below that point to honor that control valve pressure drop in that terminal unit, and that far reaching unit, if you will. And again, that's typically when you're going into that software selection, and they'll say, hey, variable speed, okay, what's your control head? And they'll type it, type in 15 feet, 22 feet, whatever that number is, usually a percentage of maximum. So that when it builds that system curve, which it will do, automatically in the software, that's your starting point. So that pump's always going to develop that minimum pressure differential head. And then from there, it will vary to the point where you finally get out to design condition, which again, like we stated, is a rarity. It's not a common point to be operating at. You can get there, and when you do, you do. Most of the time, it's somewhere significantly less. So just kind of pressing on here, get everybody out of here. All they're talking about this next step, and we kind of touched on it already, but that control head. So variable speed pumping with a terminal control head. And so, they're talking, I got a duty point or whatever, 500 gallons a minute at 75 feet ahead, and point achieved by varying the speed from the 60 hertz. So technically, instead of a full RPM and 60 hertz, it's dropped down to, I guess, technically about 58 hertz. But the point here is just that the curve, the system curve, sometimes they'll actually call it like a control curve, because they're saying, hey, I've got this control head of 20 feet, control head minimum pump differential for terminal units. So I'm starting at 20 feet and then varying up to my design conditions of that 500 gallons a minute, 75 feet. So as you get into applying variable speed, there's, I guess, a couple of different methodologies, if you will. And when we finish this, we're going to jump into some of what's becoming pretty popular, in the right application, where some of the VFD stuff is kind of built right into the pumps. But curve control, what are some of the strategies? You can use factory generated pump performance map, and it's monitoring motor power and torque change. So it's kind of built right into the pump itself. Sometimes even on the pump itself, they'll have some additional pressure differential sensors that put across the pump suction and discharge. Excuse me, but it's all kind of self-contained. And then some of the applications, not limited to, but these are just some of the reasons. Some of the applications that might be the most popular reason is retrofit, adding to an existing system, where it might not be easy to run that control line, that remote DP sensors in the building. So curve control, the performance curve. It's kind of a busy drawing here, but what it's showing is a couple of boilers or chillers, primary, secondary, air separation, air management, secondary loop pumps, variable speed, variable volume, with a drive, maybe some type of minimum bypass for the pump. And then we've got these numbers here, if you will, just applying some pressure drop. They're saying supply piping pressure drop is about 28 feet. Return piping pressure drop for the system is 28. And then the branch, the control valve pressure drop is a total of 24 feet. So the secondary pumps the size for 1,115 gallons a minute, 80 feet ahead, which is 28 and 28, 56 and 24, so 80 feet ahead. But developing that curve, that control curve, and here, instead of calling it a system curve, they call it a control curve, but it's starting with that 24 feet of built-in pressure drop on that terminal unit, which was this guy back here. And they're just picking the furthest one. It's pretty common to get to that far reaching, if at all possible. But what they're saying here is, okay, the total design head is 80 feet, but the constant is going to be 24 feet. We're always going to have that minimum pressure differential of 24 feet ahead. And then a variable distribution head loss of the 56 feet, which is the piping and maybe some of the terminal units. So the way it's piped primary, secondary, it's just the distribution pumps. So they're just seeing the piping network that's feeding out to these terminal units. So again, there's that system curve scale 5, or that pump affinity law talking about the change in head based on the change in flow. And you can map a system curve or a control curve. So what they're showing here is this is the kind of the variable head loss. As you're changing the flow, you're changing the pressure drop. we have this built-in, we're not going to drop below that 24 feet minimum control head. So really, when you start to apply it, what we're showing here is here's the variable head loss, and here's our constant 24 feet of control head or control branch head loss. Some of the inputs that are needed to create the control, what they're saying is, hey, what's our design conditions? What's our design flow? What's our design head? And then what's that minimum control head? So in this case here, someone might be plugging in, 500, whatever, 1115 at 80 feet ahead, and our control head was 24 feet. So some of the information that the drive needs to map. And then this is just showing a couple of maybe pumps in parallel, base mounted pumps with their own drives with some remote feedback sensors, whether they're whatever the signal is, 4 to 20 or 0 to 10, coming back to the pump controller. What type of feedback sensors, how many sensors, where do you locate them? These are just things, we're not going to answer them tonight, but these are the things that you wrestle with when you're getting involved in laying out and designing. Again, what type of feedback sensor, where do you locate it? Common sensor options, we can just use pressure, a set point pressure that I want to maintain. That might be like a pressure booster application. So I'm not really looking for a differential. I'm looking to maintain a discharge pressure at X. This would be more common heating and cooling for, HVAC applications, a differential pressure change in pressure between 2 points. Usually that remote, or as remote as we can get it across that terminal unit to maintain that 20, 25, 24 feet, whatever the minimum control head is. Temperature, change in temperature at a single point. Pretty limited application, but it's out there. Differential temperature, so change in temperature between 2 points on the air or water side of HVAC coils. Differential pressure feedback location. Where do I locate it? Mechanical room, 2/3 of the way out, or ideally the remote hydraulic head loss circuit the pump will serve, the critical circuit. So you get kind of 3 different options. Yeah, there's probably more options, but these are 3 scenarios. And what's the positive, what's the negative, or what's the ideally that's probably the least effective, but it might be the easiest. can hear me? Okay. Get out of that and get out of this. I want to get to. Can you see that, Will? It's still up. Okay. Screen sharing has stopped as the shared window was closed. Oh, well, that could be it. Share. You can see a remote. Okay, thank you. So anyways, some of the technology, relatively speaking, it's new. And all we're doing is it's still all variable speed pumping. It's just that you're kind of getting into this terminology, smart pumps. So a pump, maybe a high efficiency motor, put a VFD on a wall, make it all connect, put some remote sensors. That's a VFD package, and we're doing it for years and years. As technology continues to move forward, if you will, they're kind of taking some of that and kind of packaging it and putting it right on the pump. So there's intelligence right on the pump. So they're showing a couple of different model numbers or modes of inline pumps, some base-mounted, traditional base-mounted pumps that now have some pretty good intelligence right on board, not doing the remote wall-mounted, and even some of our inline, vertical inline pumps that will have this intelligence on board. But they're just kind of pushing the motor efficiency classifications and the ratings. And so I think it was a few years back now, but International Electrotechnical Commission, IEC, come up with these standards. So you have an IEC 3, IEC 4, and currently this is like the super duper IEC 5. That's the highest rated efficiency motor at the moment. Premium efficiency motors with the drive typically classify as IEC 3, which is still good. It's just some of this other technology is taking that efficiency and adding a point or two or a couple of points to it. So you'll see it IE3, IE4, IE5. Where I come across some of that terminology looking at pump specs and selecting pumps. So EcoXLs, this is Bell and Gossett's version of an ECM. So electronically commutated magnetic motor. So what's different about the pumps? Right off the bat, and that's what ECM stands for, electronically commutated magnetic motor. There's actually magnets literally mounted on the rotor of the pump, on the shaft. So a permanent magnet on the rotor eliminates the need for input power to magnetize because the magnet's there. The motor is microprocessor controlled, so there's a drive on board the pump that will control the operation. And then the power is pulsed on and off electronically to create that magnetic field in the stator. And the process is known as commutation. So electronically commutated magnetic motor. Just a quick clarification. Some of our traditional three-piece or inline pumps are now being manufactured or shipped with ECM motors. So it's an ECM pump, but just because it's an ECM pump, it might not qualify or classify as a smart pump. It's got an ECM motor and it can do some speed control, but it's going to need something, either a signal, external signal coming to the pump, or playing with like on the motor itself, they'll have like this little gauge or potentiometer where you can select a particular speed, and the pump is capable of changing the RPMs to whatever you select. But it doesn't have some of this stuff, these drives on board. So the ECM pumps, so they're a step up, but they need some external setting or signal coming into the pump to respond accordingly. These guys, they have the drives. This technology has the drives. And what's interesting is you have this one pump with a computer on board, a printed circuit board, and because of that, you can do all of these different modes of operation with the same pump. So there's a lot of flexibility. So the single model can do proportional control mode, which means, pump senses a reduced flow. You're out with a bunch of zone valves on fan coil units. As those zone valves are opening and closing, the pump can sense this and change the speed automatically. Constant speed, you can dial in a particular RPM, a particular speed. So you can take this pump that has all this capacity and you can set it to the application. So it doesn't consume any more energy than what's needed for that particular application. Constant pressure, you can get into delta T mode, where you'll maintain a constant differential temperature. Constant control mode, vary the speed of the motor to maintain an internal pump sensor. So on board the wet end of the pump, right behind the impeller, there's a temperature sensor. So you could use it, like sometimes we'll use them on domestic hot water recirculating lines. Maintain 105 degrees, maintain 110 on that recirc line. It's on board. It's right there. That's an application. Yes, sir. CNO. This last one here, analog input. So I can take the pump, not I, the pump can receive a 0 to 10 or a delta T across the heat exchanger. Yep. Maybe maintaining a certain delta T across that heat exchanger, return water, what's leaving as it's modulating its firing rate. And if you say, hey, maintain 20, and that 20 starts to do this, then I'll send a stronger signal to maybe speed up the pump. And if that 20 gets tighter, because the firing rate's starting to reduce the BTU output, the flow's too high, I'll reduce the power signal to the pump, which controls the speed, the RPMs, like we just talked about, RPMs affects GPMs, and I'll reopen that delta T back to that desired, say, 20 degree across the heat exchanger. So that's how it's happening on the boilers. But the beauty is just one pump can do a whole bunch of different applications. So they'll have this onboard drive with a printed circuit board. It's a simple little picture, but it's sometimes you say a picture speaks 1,000 words. All they're saying is I have this microprocessor that's electronically pulsing that power on and off. And so the north and south pole, the north being the green and the red being the south, as the microprocessor pulses the power, the magnet goes chasing. And it's just trying to catch up, and it never can. So the faster you pulse it, the faster it's spinning and increasing flow and required horsepower. But more importantly, or as importantly, as the load's changing, I'll change that pulsing. I'll slow it down, which reduces the horsepower and the kW required to run that pump. So it's constantly, it's variable speed. It's just on board. They have limitations, meaning their capacities. They're only up to, in this particular style of pumps, they max out at 3 horsepower right now. But you look at some of the flow rates and you have these, they call them different categories. They'll call them the high head performance range and then the high flow. But you get into some pretty high flow rates, and you're moving 2.5, 3 million BTUs. I mean, you got some pretty decent performance on these self-contained inline smart pumps. Some of those modes, real quickly: proportional pressure. All it's referring to is the pump pressure continually adjusts itself based on the demand, what's happening. So if I'm in a system where I have a bunch of zone valves, control valves, feeding whatever, baseboard in an apartment building, fan coils in an office, whatever it is. This is a pretty good application where I could take that pump, depending upon the size of the application, and set it for proportional pressure, and it will constantly adjust as the system's opening and closing its zone valves, its load. Just real quickly, so when you say proportional pressure, what I'm saying is I have one distribution pump, and then I have all of my terminal units have some type of control valve. Simple drawing, 4 of them. But what's kind of interesting here is this little visual, it's a little cartoon, but it's saying the onboard, the PCB, the printed circuit board, has the operating curve stored. It's printed, right? It's in its memory. So he knows where it's supposed to be in terms of performance. And as soon as some system conditions change and that pump starts to move off of where it's supposed to be, it will adjust. So what it's trying to show here is a very simple application, but I got 4 zone valves. And I'm operating on pump curve 3, we'll call it, and I have all 4 zones open. Now, as a zone closes, what would happen is traditionally on those pumps that didn't have this drive capability, it would start to back up on its curve. Now what I'm doing is I'm sensing this change and I'm slowing down that pulsing, that commutation that I'm doing. So I'm slowing down the RPMs and I'm staying on this printed circuit, this pump performance curve. So I back down. And as more zones close, I just follow down on that curve. Now it looks pretty simple and all, but that's pretty good stuff in terms of saving energy, and it's all built in on the pump. So that's all. It's just a visual showing what proportional pressure is all about. Yes, sir. Oh, sorry, CJ.
How much of the calculation of the person designing the circuit, how much you're given
What would happen, like on this right here, when you're in proportional pressure,
yeah,
they have this thing where you have what you would select like the design condition. What's my design set of conditions? Flow and head.
yeah,
In proportional pressure, and it's just it's a logic that's been accepted in the industry both in Europe and then worked its way over here to the States, is they'll take whatever that maximum pressure, whatever that design head loss is, and they cut it in half, divide it by 2. And so that becomes my low point. So that's my range that I can work within. And so as the flow requirements start to be reduced because valves are starting to close, it's backing down, it's slowing down its RPMs, providing less flow, but it doesn't go all the way down to 0. It'll always maintain that whatever that design head divided by 2. And so that happens automatically in proportional pressure selection as that mode. They won't, yeah, everything's calling, correct. Oh, I see what you're saying. I see what you're saying. Well, yeah. Yeah, up here and back it down. Right. Curves, right. Calling, right.
okay.
So that range really should be more reflective of all zones open.
Those red lines kind of arbitrary, right?
Yes, anywhere in between. Correct. That's right. Yeah, correct. That's right. It's as simple as that. That's a great statement. So all this was is just it was trying to highlight like a particular, mid-range light commercial circulator. One of the interesting things, which was kind of the first time B&G's done it, not knocking them, just something to comment on, but like the model number XL 65-130, it actually is referencing the maximum feet ahead it can develop and the maximum flow rate. Kind of the first time the model number actually had something to do with the pump curve. So if from your mind's eye, in a way, you can say, okay, at no flow, zero flow, I can develop about 65 feet ahead. And then at no pressure drop or very low pressure drop, my maximum flow rate's about 130. So here's my curve, just from a visual, and I can operate anywhere in between there and depending on the application. But what I was just trying to highlight here is whatever that maximum flow and what that pressure drop, whatever it is, 20, was it 20, 25, 30, 35, 40. So somewhere around 35 feet ahead or whatever. And you were in proportional pressure, you'd cut it in half and say, hey, I can go from 35 feet down to 17 or 16, 17 feet ahead.
This is from
The remote just on board, right? The logic. and the point being, it's speed control, right? So we keep saying the same thing, the beauty of RPMs, controlling the speed of the RPMs. Right. Yeah, about changing the speed. And the other interesting thing is these pump curves, like the next curve that they'll show us, is power consumption. And that's the meat and potato, so to speak. So that curve that doesn't look all that, okay, it's reduction. You have them cutting through different RPMs. When we start looking at the power consumption on that exact same curve, you're going from whatever, 800, give or take, watts, and depending upon performance, what's happening in the zones, and they're closing and this thing's backing down. You could be down around 300, 250, 200, 220, whatever. So that's the beauty. And that's why the drive or the interest. And so on those smaller applications where I have these, and we do it all the time. It happens both in the boiler room with the boiler pumps, and then you go to the distribution going upstairs to the condos, the apartments, the dormitories or whatever that have some type of zone valves. With this application, so without that need, like Will was saying, of having maybe put that remote, as you get into the bigger applications and that's part of the package. But on these smaller applications, you're getting a lot of the benefit and a lot of that energy savings, and it's all right on board. And the beauty is that pump can then be used in the next building or the other application or down the street or whatever. Maybe it's delta T, maybe it's constant pressure, maybe it's constant. So you have all of that capability on these pumps. Constant speed. And all it's saying is the pump will maintain a fixed speed at any flow demand. So constant speed. Desired set point can be programmed right at the pump. So, in this case here, maybe there's zone pumping. And those zone pumping can be for whatever the application is. A building, a coil, a heat, whatever it is. The point being is it's not one pump with a bunch of zone valves. And those valves are open and closed and the pump's got to adjust. This was saying, hey, when I turn on, this is where I'm going. Well, instead of just getting this pump, and maybe it's oversized or more energy than I need, I can dial that speed down to what is the load? What am I doing here? Every time I come on, I don't need to consume more than X, what I need. And that's it. So it gives you that ability to dial that in. And constant pressure maintains. Yep. Yeah, they can communicate with each other. Right. We were just showing just a quick, someone taking a picture of an install, and kind of to Will's point, we're just going to jump into it right now. I have these two pumps a certain size. You can see them plumbed together. So one distribution, so it's a standby pump. One's operating, one's standby. And that would be most likely the larger one that's probably going out to all the apartments upstairs. So whatever the load is upstairs. And then the other two guys, they're feeding domestic hot water tanks. So when there's a call for domestic, again, not a bunch of zones, it's going through a coil. In fact, if you just turn around and look real quickly, but right there against the wall, there's a cutaway of a tank. So it's showing a coil inside there. So when that pump comes on, he's just taking boiler water and he's going through that internal coil and back. So it's a fixed, but you can dial that pump in to whatever the requirement the manufacturer of those indirects says. Hey, I need 15 gallons a minute on, and I got 3 coils. Okay, you need 45 gallons a minute. You got to overcome the pressure to all. And then the other thing is one's going and one's backup. One's going, one's backup, and they can communicate with each other and they can talk to each other. So right here, we'd wire from one to the other. And so that now the two pumps know each other exists. One's kind of the boss and one's the member or whatever, the partner. And you can get into these modes of operation. And again, same pump, two pumps in this case, and they're all capable of doing this. And so you have these very simple, just backup operation. I don't want to rotate. Only the lead pump runs. Kind of a weird application, but it's there as an option. And the second pump starts in case the lead pump fails. This much more common alternate operation. Only one pump runs, but it's switched. So the lead guy switches every 24 hours, equal runtime. And then the second pump also would start immediately upon failure of the guy that's supposed to be running. So that's where maybe you start to eliminate that pump sequencing third-party need. It's built in. Another thing is an option. It takes a little bit of little gray matter, but you could take two pumps in parallel, right? So you have this load. It's whatever the flow rate is, 500 gallons a minute. You could take two 250s, run them in parallel, 250 together, 500 gallons a minute going out to the building. And then there's a little bit of intelligence on board here where it's saying both pumps run simultaneously at the same set point. But as the load upstairs changes and it starts to reduce, the lead pump can either start or stop the second pump to satisfy. So you could actually back off one of them and just run on the single pump because that can carry the load. And then as the load increases, that lead pump senses that change in pressure, what's going on in the system, and he brings the parallel pump back on, and the two of them are running together in parallel. So there's a lot of intelligence all on the same pump. And then the last mode is just force, with there's none of this logic, if you will, and they just both turn on and they run all the time. So you get a lot of flexibility just by running a communicating wire between the two pumps. And that's what they were trying to show in this drawing here. Can't see it all, but these two guys were talking to each other for the building distribution. These two guys were talking to each other for the domestic hot water application. So anyways, and again, just, you get some interaction. I guess they use a fancy term. They'll call it HMI, human machine interface. But the point being, hey, STBY, standby. So I'm standby, and this is the guy that's running right now. He's moving 36.5 GPM. You could sit there in that basement, you could hit that button again, and you could see the feet ahead, hit it again, see the speed, and hit it again and see the watts, what's it consuming. So it gives you a lot of information right there in front of you. And this mode here, this one's lit up. This is saying, hey, proportional pressure. Because what's happening upstairs is like probably 36 apartments with 36 thermostats and 36 zone valves. So as they're opening and closing, this pump's speeding up and slowing down and responding to what's going on upstairs. So a lot of capability and intelligence just in a simple application. And then again, the temperature dependent, you can use an onboard sensor, and then you can have a remote, and you could have a Delta T application, perhaps. That's what they're talking about. So whether you choose to use it or not, it's a lot of flexibility there. And then this last one here is just about this analog input. The pump has the ability to take this external drive, this external signal, which will then influence the speed of the pump, 4 to 20 milliamp or 0 to 10 volt DC. And this is where it's becoming very popular on boiler pumps for these condensing boilers, X number of BTUs, 500,000, 2 million BTUs, whatever the application is. Because again, just like we talk about the maximum flow rate for that design set point, well, the maximum output of the boiler plant is probably needed 3 to 5, 6% of the heating season, and then something less the rest of the year. So I can start to change flow rates, and we don't need to go through all the exercise at the end of the day here, but what it all is trying to talk about is when you have fixed speed, you can create scenarios where you're over pumping the boiler plant to satisfy, say, a secondary load out in the building's requirements for water temperature. And the downside to that would be as I over pump the boiler plant versus the distribution, the secondary, I'm taking some hot boiler water and I'm mixing with my return water coming back from the building. And when I'm dealing with high efficiency boiler plants that condense, I want to try to avoid ever taking really cold water and making it a little bit warmer, because I start to affect the efficiency. I start to reduce the potential. And so by having fixed flow rate, I really can't get around that. So the whole little exercise here is just to lead up to saying, hey, if I can keep this water as cold as possible, I really can influence the efficiency of the boilers, the firing of the boilers over the course of a day, a week, a heating season, 5 seasons, add it all up. So what they're trying to say here is instead of using this fixed flow, and what happens is when the boiler has a maximum capacity, so in this case here, it's a 500,000 BTU in, 467 out, I have a flow rate on a 20-degree Delta T, 47 gallons a minute. It's fixed. It's a fixed speed. And I need it when I'm firing at full flow. But as the boiler reduces its firing rate because the load upstairs changing on a fixed speed, what happens is the GPM stays the same and the Delta T across the heat exchanger gets tight. And in getting tight, it can lead to short cycling of this appliance. And typically, when you have these high efficiency modulating condensing, I want to bring them on and not shut them off. Just kind of modulate, simmer. And so what they're saying here is this is the solution, or part of the solution, is have this pump be a variable speed, the boiler pump be variable speed controlled by the logic of the brains of the boiler. And now, as I reduce my firing rate, let's reduce our speed, our GPM, to maintain a fixed, say, Delta T across the heat exchanger. Because the boiler will have like a inlet sensor on the heat exchanger, will have an outlet sensor, have some logic up here, send that signal. So it allows that boiler to be a little more efficient and not short cycling on and off. So there's a lot of benefits to controlling the speed of the boiler pumps. So we do it all the time. Just one quick comment, just as a general statement. When you get into this technology and they have magnets and you're attaching them to systems, sometimes they're brand new systems. Everything's spotless clean. It's all copper pipe and all of that. Then other times, the real world, it's maybe some existing steel pipe, little iron oxide out in the field. And all of a sudden you're putting this big magnet in line. And what can happen is you can collect the iron oxide and can damage these pumps. So kind of like the third leg of the stool is high efficiency boilers, high efficiency pumps. Now let's put some type of magnetic filter in line, just as a general statement, something to be aware of. Years ago, we probably didn't do it because we weren't putting magnets in the system. We were doing this different technology. As this technology is being accepted and embraced, we just want to make that last step is maybe protect. So these boiler mags or these different magnetic filters are like the sacrificial lamb. They're intentionally there to grab all that iron oxide to protect so it doesn't show up on the heat exchangers of the boilers or in the volute of the circulators. So let me just show, there's just a quick example, but typically on the return coming back before you get to your boiler and your boiler pumps and your distribution pumps that would be over here. And again, there's different sizes and different that. The point of it all is these iron oxides will just get attracted to that. And it's amazing that picture there, that's going into an existing building and like a week later, they come back and inspect. So pretty aggressive. Now, over time, that becomes less and becomes less and becomes less, gets cleaner and cleaner, which is good. But it's protecting your investment. You have these high efficiency boilers with these stainless steel heat exchangers. You have these, relatively speaking, efficient and investment on your high efficiency smart circulators. Protect them. That's all. Yeah. Clean, right? Yeah, right.
We're able to do that.
Yeah, that it got passed because the magnets got so covered initially, they lose their mag. Yeah, right. So then, like Will said, some of it gets past it. Now it's so okay. So existing,
For them to drain down
yep,
so that the whole
building,
it's like, it's rare.
pulling teeth. Yeah. They want to valve it off, keep everything filled, and then attach and go. Right. Yeah. Right. Yeah, I know. I was just gonna say, correct. And that side stream, Willie, that's what the, right, right. Yeah, it's not being sold as an air separator. Correct, correct. It's a pretty good marketing, job. Not knocking it. It's just, but yeah, it's just not maybe as effective for what you're really trying to provide for your client, your customer.
You've got like a South Street filter for kind of the
By adding the cleaner, putting it in suspension, right? Yep. Just to, yeah, to clean it, right, right. One last thing, just and all it is it's the kind of the latest, if you will, of taking that, what we were doing with the smaller 3 horsepower and under, they're now applying to, what's it go up to 30 horsepower? Well, the Hydrovar, the 30, right? Yeah, yeah, okay. So they're showing a couple of quick examples, but a base mount of 1510, and now having this intelligence, this Hydrovar X, they call it, or the Series 80, E80 with the Hydrovar X. So again, it's having that microprocessing, that capability with all kinds of, right, right, as far as, It's decoupled from the system water, right? System water. Yep. Right. They actually, I think they talk about that, Will, don't they? As far as, well, I'm just going through it, but don't they have like on board in that drive, they have like a fan that's assisting with some of that cooling? Yeah, 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 on the back end, right. But anyways, it's all the highlighting here is all of the kind of historical or the benefits of using a base mount of 1510 general features, and then added this in highly or higher efficient, highly intelligent capabilities. Longevity. Yeah, longevity. Right. So main thing, just wanted to make you aware, but got some pretty good ranges. Um, up to whatever 1600 gallons a minute, 400 feet ahead. I mean, there's all different curves again, low speed, and then the high speed as far as the RPMs. Um, Control modes, similar to what we just discussed with that ECM or those eco inline water lubricated, but constant pressure, proportional quadratic pressure, constant flow, constant temperature, all of these capabilities on this drive. And has the ability to get into parallel pumping where you can, the control logic has the ability to talk to up to 8 pumps, which is probably not that common of an application, but it's there. But the
procedure
say it again.
is the procedure to control it.
I will let you. Right. I'm sorry.
So these extra were replaced.
Yeah.
What's the price differential between this
The labor. Yeah. There's gonna apologize. Yeah, they reference that. What I forget how they. Uh, A different brand, yeah, okay. Okay, sourcing them now, right, changes. I guess that's probably a pretty good visual of what you were just asking, going with that traditional with the wall mount, and replacing it physically, yeah, right, right. Um, and it's just a, whatever, couple of snapshots of, an installation fairly recent. So obviously oops, obviously an existing building, and they were just taking out the old and putting in the new. Um, so anyways, and that service manager, they're just actually programming, that Will was referring to have the two pumps, set them up for the application, have them communicate. And Jerry likes it, and that says a lot. And then just the same thing, it's available in that Series 80 E80X, they call it, so the vertical inline. No, no, keep going. I think that's what they're trying to just separate quick connect components allows, replacement of the drive and the motor independently. So pretty quick, dead in the water. Um, yep. Moving. Right. Right. So anyways, and the same thing, performances in the low speed and the high speed, you got some pretty good capacities up to 1,400 gallons a minute. So you got some, what are they? I think it's 30 horsepower is the max at the moment. Now they're just trying to compare maybe an older E80 IPC and then to so just space saving, taking up a little less room in the mechanical space. Long day.